presentation session of the postdoc day of the institute. So the next speaker will be Luis Veilla. So Luis Veilla, it's a graduate student from Universidad Complutense. Then he did a master in astrophysics also in Complutense. Then he made his PhD in in CAB under the supervision of Carmen Sanchez Conteras and Jose Cernicharo. So after his PhD, he made a first year of postdoc here in the institute before going for 3 years or so in Gothenburg in Sweden. And now since
2021.
Since 2021, he incorporates the institute again with a gene contract, and now he will speak us about chemistry in outflows of post-RGB stars. So you can start.
Thank you, Alex. And first, thanks to the institute for inviting us, all the postdocs, for giving us the opportunity to present a bit of our work. And also thanks to you for devoting some time to be here and hearing us. So I'm going to talk about my GIN, in Spanish GIN, not GIN, because it's Jóvenes Investigadores, Young Researchers project. And the title is CHIPS, so the acronym of Chemistry in Outflows of Post-AGB Stars. For all of you that doesn't know what an AGB star is, I'm going to talk about that. But the acronym is Asymptotic Giant Branch Star, in Spanish, Rama Asintótica de las Gigantes. So, to start, and also thanks to Miguel, because he has introduced some concepts that are going to be useful for me, like the how we use the Doppler effect, and also what is the angular resolution related to the size of a disk or a telescope. But I'm not talking about galaxies. I'm going to talk about another important element of the universe, which is stars. So I think most of us have a very basic idea of what a star is. So a star is a self-gravitating ball of gas and plasma. It's like a thermonuclear reactor that is synthesizing some materials because they're fusing elements into heavier elements. And in particular, I'm going to focus, or my project focuses on one special. Okay, like this. Okay. So I'm going to focus on the late type of stars. So these are M-type stars. So we classify stars, of course. The most important parameter that defines how a star is and their properties is the mass. But the way we classify is due to their temperature and luminosity through the spectral class. And I'm going to talk about M-type star, which are one of the coolest stars we have among different stars. So these stars, well, what we have here is the Hertzsprung-Russell diagram, which is the most important diagram for an astrophysicist. So we are representing the surface temperature of a star against its luminosity. And in fact, like we have here a still picture, but this represents like the tracks the stars will follow during their evolution. Most of the stars or they spend most of their life in the main sequence, like our sun. They are burning hydrogen into helium in their cores. But then all this hydrogen will be exhausted in their interior, and then they will have you have a balance between the gravitation and the thermonuclear reactions, and they will contract to increase their temperature so they can continue fuse helium, and then they ascend different branches, what we call the giant branches, because they increase their size like a lot. For example, a red giant star or an asymptotic giant branch star can be as huge as the orbit of Mars or the Earth. So you have an idea of what we have. And then, well, after some thousands of millions of years of evolution, they will become hotter, and they will develop a planetary nebula, and then they will end their lives as white dwarfs. So in terms of the basic picture of a stellar evolution, or the most accepted stellar evolution picture we have, is we start from a molecular cloud, like a cloud of gas, and this will contract because of self-gravitation, and then also some magnetism, also turbulences. They will contract to form a protostar. This protostar, after years of millions of years of evolution, you will have a main sequence star, like the sun, as I have said, and then you will have two different paths. So one big path will be for the low intermediate mass stars, and the other path for the massive stars. And that is defined by the mass, as I said, is the most important parameter. So if your mass is below 8 solar masses, you will follow this path. And if your mass, the mass of the star, is more than 8 solar masses, you will go this path, okay? So what I have studied, also I participate, like for example, with Guillermo, which is also a researcher from the IFF. He does the massive star part, or he's more focused on this part. I do more research on this part of the stellar evolution, and particularly in these two stages. Well, also in planetary nebula, but these two stages, the asymptotic giant branch. And it's called asymptotic giant branch because it's like a parallel line, like the giant branch that we saw in the HR diagram. And post-AGB because they have left the AGB branch. And what is important in the evolution, we saw this is a linear picture in the last slide, but this is like a cycle of matter. So we form a star from a pre-stellar cloud, and then the star will evolve. It will follow the path depending on the mass. But then when it's about to die, this star is about to die, they left some matter that they have synthesized and processed during the life, and these leftovers from the star will form again a prestellar cloud. So you are enriching continuously the universe and the medium with synthesized matter from the stars. And this is the most important part of from my point of view, of the role of dying star in the evolution of the universe and in the stellar medium. So, as I said, during these late stages, they start to inject matter and also energy, but this is most important for the massive stars. They inject a lot of energy to the medium when they explode as supernova. But we have 2 points two ideas we have to keep in mind. So the bulbous stars are main agents of the interstellar medium enrichment in terms of gas and dust. And also the synthesis of matter in the stars and in their envelopes increase the chemical complexity of the ISM and the universe. That's why it's so important to study them. And just to put some numbers so you believe what is their significance or their role in how they enrich the medium. So in this table, which is adapted from a famous book by Alexander Thielens, I represent here some objects, and I'm excluding, of course, here the circulation of matter from the halo of the galaxy to the disk of the galaxies, and also exchange of material from other galaxies. But inside our galaxy, if we measure the input in terms of gas mass and dust particles, we have carbon dust and silicate and metal dust. We see that oxygen-rich giants and carbon-rich giants dominate this input to the interstellar medium. So that's why it's so important to study them. And this is not only something that, I mean, feel yourself included in this picture of the evolution of the universe. Probably you have heard this sentence that we are made of dust of stars. But this is true. That there are research about comets from the solar system. They have studied these isotopic ratios, the composition of these comets, and they have found that some elements cannot be formed in other different stars than AGB stars. So what happened, probably a first generation of stars evolved until the AGB. They left over their material to the medium, and then this again form a molecular cloud that form a pre-solar system and then a type of solar system. So these grains are in fact formed in AGB stars are in fact in our solar system. And one thing that I have to highlight, so I don't really, my research obtains, gives information about the stars we are studying, but my research is not focused on the stars itself, but on the circumstellar material that surrounds the star. So you have to form this circumstellar envelope, and the way you form this circumstellar envelope, or the most accepted mechanism to explain the formation of a circumstellar envelope, is this scenario represented here, which is called the Pedro scenario. So it's a pulsation-enhanced driven wind scenario. So we have a giant star, which is, as I said, as large as the orbit of Mars, but roughly its mass is the mass of the the mass of the Sun. So these stars have a very low surface gravity. Okay, so the material in their surface, if somehow you get some mechanism that ejects the material, it's easy for this material to leave the star. Okay, and due to the configuration of the external layers of the star, you have like fusing hydrogen in cells that occur periodically. So the thing here is like an engine. So you are fusing hydrogen, and then the gas expands. As the gas expands, it cools. So you lose temperature, and then the fusion of the hydrogen is not effective anymore. So they contract, and then it gains temperature. So you have a pulsation, then have a mechanism of pulsation in the stellar exterior, and that will help all the material in the atmosphere of the star to be ejected. And the conditions in the atmosphere is very low temperature, very high density, so you favor the formation of molecules. Molecules that, depending on the temperatures and the condensation temperatures of the different materials, will form sheaths of dust grains. So you will form dust grains, you will have molecules, and as these stars have very high luminosity, the radiation pressure acting on the dust grains will push away all these dust grains, and in this way out of the dust grains, they will drag the molecules, forming the stellar wind, the circumstellar envelope. In terms of chemistry, what we see, well, standard chemistry, what we see is two types of chemistry. As I said, the material we have depends on the mass of the star. So depending on the mass of the star, you will have a carbon-rich star or an oxygen-rich star. In general, you expect in the local universe the oxygen is more abundant than the carbon, but in some cases you will invert this ratio. And if in the case, well, in close to the star, you will have a chemical equilibrium. Of course, this is an approach because it's a dynamic environment and you will have other processes, but in principle you expect it will be dominated by chemical equilibrium, and then you will have for oxygen-rich star this kind of a species, and for carbon-rich this kind of a species. Then in the outer part of the envelope, this is exposed to ambient light, and that ambient light means the interstellar medium radiation field, and this is very hot stars that are illuminating the envelope, so with very high energetic photons, and they will dissociate the molecules, and you will obtain what we call daughter species, and which are photoproducts. Most of them are photoproducts of the parent species forming here. Here you have like an idea of the physical parameters we're talking about in terms of distance and temperatures. And this is, of course, you don't have to read everyone, but it's to give you an idea of what has been found so far. And this is separated by the different chemical types. So we have carbon-rich envelopes in blue, what molecules have been found in only in oxygen-rich envelopes here. And then this is not updated. I have to apologize for that. I mean, it has, I think 1 year or 2 years of delay. So probably we will have to include more molecules here. And then we have molecules that are shared between both chemistries. And also we have S-type stars, which are stars that have a ratio, carbon-oxygen ratio, which is close to 1. And I have to say that, in fact, well, nearly half of the molecules discovered in space have been found in a very famous carbon-rich envelope, which is called CW Leo, or IRC 10^16. And in fact, I would say like probably 80 or 90%, I don't know the number, but probably 80 or 90% of molecules found have been found by Pepe Cernicharo from the 80s. And one of the interesting questions that emerges from this research is, well, of course, we have a very naive idea of chemistry, and then carbon is more active than oxygen. of course, but it is really the molecular content, or is this an observational bias? Because IRC 10-16 is very easy to observe. It's close to us, it's very bright, and probably we revise the number of hours observed with a telescope that source. It will be like, I mean, comparing skyscraper with a very low building. So we have devoted more time to observe IRC 10-16. So one of the questions that emerges is what if we also observe other sources like oxygen-rich sources, and we investigate their chemistry. And then we have also the evolution towards late stages rather than the AGB. So as you evolve from the AGB, what it will happen, the star cannot be losing mass during all its life. It cannot be sustainable. So at some point, the mass loss will stop, will cease. And then the envelope will detach, all the material will be lost in the interstellar medium, but the star itself, due to limits on their mass, it won't be fusing carbon, oxygen, and other products. So it will form a core that it becomes hotter and hotter and hotter, and then you will get a lot of UV emission, so you can dissociate molecules from the inside. And during all this evolution, you will see chemistry that departs from the standard chemistry. One is related to shock chemistry. Of course, this happens also during the AGB because you have this pulsation. So you have inner envelope pulsation. This is material shocking constantly your gas and your grains. So it can be extracting material from the dust grains. And also in this evolution, what you see here, this is around this envelope on the AGB. And this is the Calabash Nebula, a post-AGB. You will have the interaction between the AGB wind and the post-AGB evolution. We don't really know what happens here. In this case, probably is induced by a stellar companion. So we have a binary system that is causing this bipolarity. But also, there are other researchers that investigate if this has to do with the magnetism or other mechanisms that can induce this bipolarity. And in terms of photo-induced chemistry, we have, as I said, the evolution of the central star. But also, if you have a companion, you can have UV emitting companions or even higher energies. We are in a project now studying about the X-rays, for example, and their role on the chemistry of these stars and these envelopes. So if we want to observe the circumstellar medium, and we are talking about the molecular gas, we can, of course, observe in different wavelengths, and we will observe in the optical, like this is CW Leo, the star I talked about before, and the Calabash Nebula, seen in the optical. As you can see here, I mean, the star, you don't see the star. What you see here is all these arcs and circle is the dust, which is blocking the visible light. So the star is embedded in that circumstellar envelope somewhere inside. And the same happens here. You see here there is a black disk here, which is a thick disk of dust, which is obscuring all the light that will be emitting the star. And in fact, all this light escapes through the poles of the disk and it gets reflected by the nebula. So you see the reflection nebula here, thanks to the orientation of the system. But what I do, in fact, is to study the molecular rotational transitions of molecules. In particular, CO is a proxy of the whole circumstellar mass. So it's most commonly observed to study this kind of object. So this is the same object observed in visible, and this is a CO emission, probably 115 gigahertz or so, or in the millimeter wavelength. And the same for the Calabash Nebula, seen as with an interferometer. Here you have the outflow seen of the outflow of gas that is lying through this bipolar axis. And to observe that, what we do, and also Miguel talked about a bit about this, what we do is to observe with dishes, so antennas, with a single dish, like for example the 30-meter in Sierra Nevada, the Sierra Nevada, or the 40-meter telescope in Jebes, which has Salvador has talked about it and the visit to it, and also with interferometers. And the difference between an antenna and interferometer is, to summarize, we use interferometers because we want to increase the angular resolution, the spatial resolution, and as angular resolution is related to the size of the disk, the larger the disk, the larger the angular resolution. But of course, this is restricted by engineering. You cannot build an indefinitely large antenna. There is a limit because you want a movable antenna, and then if you have a, I don't know, 80-meter disk, you won't be able to keep that in place. So what you do is a trick. So you mimic a very large antenna by collecting many antennas, and then you produce like a disk, of course, with holes, and then there's a trick with interferometry, so you can recover the real image with a much larger angular resolution. And what we obtain is maps and spectra. What we do with maps is like a tomography. When you go to a hospital and you get this tag, this axial computerized tag, so you get the slices of your body. It's the same here, but of course we use the Doppler effect because what we have is information on the plane of the sky, so the 2 dimensions, x and y, but you don't have information on the line of sight configuration. So you have to assume that your object moves with a given law, and then you can transform that to a given spatial configuration. So you recover from velocity, you get a 3D reconstruction of the object. And also spectra. So in the millimeter wavelength range, what we get is rotational transition, lines of rotational transitions in vibrational ground states, and also excited vibrational states of different molecules in the envelopes, in these circumstellar envelopes. And what we do? Well, of course, this is our main goal, summarized in one large sentence, but we want to first detect as many molecules as possible in space. That's a driver of our research, of course, but we want to observe how they are spatially distributed, so we can obtain information about their physics and their chemistry. And through the analysis of all this data, what we do is create models, basically with radiative transfer, which is how the light interacts with matter in your object. So you get the output of brightness distribution, and then you derive information on how your object is configured, how the matter is arranged in your object by doing this analysis. So through all this processing, you get information you get predictions of spectra and maps that you can compare with your observations, and also with chemical models. But most interestingly, I could talk a lot about what is known from these objects, since we know them from a very long time. But there's a lot we don't know. And what remains unknown is how you go from a spherical envelope in an AGB to an asymmetrical post-AGB. And that's a very key question to answer. Here you have some pictures from the Hubble Space Telescope of very nice and asymmetrical bipolar, in some cases, post-AGBs. Or for example, how you obtain this, because you expect that your mass loss is more or less isotropic in your star. But when you observe with high resolution these objects, you observe like spirals, arcs. This is an example of different AGB stars. And also this is IRC 10^16 CW Leo. You see here these arcs when you observe with a very low resolution, very low angular resolution. But as you zoom in the star, you see some anisotropy. So the mass loss is not occurring in an isotropic way. So there is a mechanism that is affecting the way the star loses mass. And from the chemical point of view, when you try with your standard chemical models, for example, this is a chemical model adapted to the case of the Calabash Nebula. Here I'm representing the abundances against evolution time. This object has the dynamical time of the bipolar nebula is about thousands of years. And then you compare your observed values. You have techniques to derive the observed abundances. You compare against your chemical models, and there is very large discrepancies in some molecules, and principally in the case of oxygen-rich stars with here is methanol, which is being represented. This is an organic molecule, and also organic precursors like the isocyanic acid, HNCO. And this was one of the drivers of the CHIPS project. So as I was investigating this object, one of the things that comes to the, I mean, I guess easily, or it was easy to me, that this post-AGV object is resembles a lot to the configuration of a protostar. So we are talking about a very different object. So this is a star that is being born, and this is a star that is dying. But in terms of their physics and chemistry, so morphologically, when you compare them, they are very similar. They have this elongated bipolar shape. When you compare maps of the molecular content, they are very similar also, and they're also the molecular content is very similar. Both have methanol, organic precursors, and they share a lot of their molecular content. And in fact, in principle, they don't have so many similarities. So there must be something in the molecular processes inside this object that it's common. So that's one of the drivers of the project. If one thing that wasn't investigated in post-AGVs is the chemistry of shocks. Even ices, maybe there are some ices, coats of ices in the dust grains that after the shock during the jet of the post-AGV jet or parts of the dust grains are injected into the circumstellar medium. All the molecules that were in the AGV envelope were dissociated, and then after some period, some thousands of years, let's say, you have some molecular reformation, and you get again new molecules, a new content. Maybe the similarities resemble in these processes, but this is something that is worth to be investigated. And not only from the chemical point of view, but also from the morphological configuration. As I said, and probably the most accepted theory now for the production of these bipolar outflows is that you have a multiple system. You have a binary star, even you have systems with 3 or more stars. But then it is proved by observations that at least low mass stars, half of all the stars in the galaxy have a binary companion. And in the case of massive stars, that number is larger than that. So it is important also to investigate how you go from a spherical envelope to a bipolar envelope. And one of our recent results is to confirm that also, because this was some sort of no with in different wavelength range, but we have confirmed in IRC 10-16 that these anisotropies occur in the very act of the formation of dust grains and molecules in the atmosphere of the star. And this has been a result is going to be published very soon in Nature. And this is just a bit of a figure from that paper where we analyze the emission. You have here emission from HCN and SIS, 2 different lines. So we compared the intensity ratio between both, and we see that there is a directional dependence from it depends the ratio you obtain. In an isotropic scenario, you will have the same, you will have a ratio that is equal depending on the direction, but this is not the case when you compare the emission in a given direction. For example, let's say from here, and then you rotate, you will see that this ratio changes. But also processing with more, I'm also doing new processing methods. So the only way you have to, as long as you enter into an asymmetric world, you need 3D models to obtain information about your sources. And here you have an object which is a HD101584. It's also a bipolar outflow. In this case, we are seeing the object not perpendicular to the plane of the sky, but it's like it's pointing towards you, a bit tilted, like 8 degrees or so. And here representing the CO emission, in blue is the emission that is coming towards us, in red the emission that is moving away from us, and in green it's a disk that is located in the, it's not moving relatively to us in the line of sight. So now what we are doing with 3D models is try to compare the observations, what we obtain in the observations with synthetic models. And this is quite complicated because radiative transfer problem in 3 dimensions is the very difficult thing, and also there are no well-tested tools to produce 3D models of your objects, and we are trying to get to that point. So now from in 10 years from now, in the past we had like 1D or 2D models, and now we are moving towards 3D to a 3D world. In fact, all the papers that are being published are now using 3D techniques. So that's also another thing I'm doing now. And a very recent result, just also to show that how valuable is this kind of research. For example, this is based on KJPN8, is a planetary nebula, and some images. Well, this is a symmetry image with the tubular shape of this envelope. Here you see the H-alpha emission. There is a disk of material inside the nebula, seen there in H-alpha. But when you observe it in molecular gas, in CO, you see there is a disk. Well, for example, in this object, there was a debate on the origin. So, as I said, you don't really know how you go from a spherical envelope to something more asymmetrical. And then there were different explanations to the progenitor of this object. And according to our observations, through the analysis of isotopic ratios, we will probably confirm that the progenitor of this object was a massive progenitor. So just to show also a bit of what I'm doing with my research. And I think I'm on time, Alex, or maybe 1 minute or so. So thanks for your attention, and on any question is very welcome. Thank you.
Well, thank you, Luis, for this very nice talk. So we have time for some questions.
You wrote in our chemical models are not good enough. We are missing some ingredients, shocks and ices, okay? I have heard many times the ices plays a very important role, but I would like to know in a very qualitative way if you can tell us how shocks and ices can be improve your chemical models.
Well, from observations, it is known that, in particular for oxygen-rich objects, from infrared spectra, you know they have water ices. But you need, there are not many research done in that field. So for example, with GWST, we have now opportunity to observe this object and see if they have other ices like methanol. For example, I have talked about the detection of methanol in gas phase, but we don't really know if that methanol is formed in the gas phase because you have compression due to the shock, and then you increase the temperature, density, and you get some different processes, or if it is because you're shocking a dust grain and then you extract part of this ice, and that gives a new chemistry. And from the theoretical point of view, and this has been done, and that's another connection done between the dying stars and the stars that are being born. The other connection is done is that in protostars they use chemical models that incorporate these ices, but this is not done in the evolved stars community, because these water ices have been found, but it's not really, because the conditions are not the same, so you don't really expect to find and ice in this environment. But that could be different in a post-AGB when you have shocked all this material, you have launched this material very far away from the star, and then maybe some molecules can condensate and form an ice. And for the theoretical part, you will need to first, well, if you want a hydrodynamical chemical couplet model, that's the matter of everything, which is a huge step to be done. Yes. So the first step that has not been that I'm aware in our field, for example, a simple model of a shock compressing all this material is mimicked, but not really incorporated in equations. So you compress the gas and see what the output you get after some evolution. It has been done, the research about how shocks affect the material in the inner parts of AGB stars, but not what I'm talking about. And the other part is the chemistry of the gas grain chemistry, which is not, I mean, if you want to incorporate that in AGB stars, that's a huge problem because you have to incorporate, as I said, the dynamical atmosphere, and then you get a very complicated couplet problem. But you can do something in the post-AGB, I think, by including this gas grain chemistry.
Okay, do we have a question?
Well, my question is very simple. I have always believed or read, etc., that stars like the sun that cannot end up like neutron stars or what holes, no, at the end of their lives, will end up, all of them, as white dwarfs.
Yeah.
So it's true then, because of course what you have shown us, all these nebulas, very beautiful thing, but at the end, all of them will end up leaving behind a white dwarf.
Yes, well, I have to make a precision because I said that the threshold is 8 solar masses. That can be 10, let's say that number. And then below 0.8, you enter into red dwarfs, and those are totally different because they don't, there are stars, and they are very frequent in our universe. They don't fuse hydrogen, they don't die as white dwarfs. But then in the range between, let's say, 1 solar mass and 8 solar masses, they will end their lives as white dwarfs. And then if you move into the massive star branch, all of them will, depending on their mass, will end up as black holes or all these exotic
So
objects.
the lightest of the lightest end up as red.
Yes, I'm not an expert of that, but I think it's the name is maybe some astrophysics colleague can help me with this, but this is I mean, those that are below 0.5 solar masses are brown dwarfs. I said red, these brown dwarfs.
Thank you for the talk. So you said that the explanation for that bipolar shape is that the thing is binary.
Yes,
and
yeah,
what I got lost was when the star is still not formed. That's still the explanation. When the star still not formed. So you showed a picture with a star that was dying and compared it with one that was not born yet.
Yes, well, in that case, if you have a single star being formed on a molecular cloud, I mean, you will have like a flare disk, and all this material at some point will lose angular momentum, and then you will get jets, and all this material will be launched in these jets, and you will get a bipolar shape in these young stars.
So the explanation worked both for the dying star and for the starting one?
For the dying stars, has been researched with magnetic fields, so magnetic fields can help in single stars to develop some kind of bipolarity, but most accepted theory is that you have a binary companion that is forming a circumbinary envelope or a disk, and this will end up as a bipolar outflow.
The point is having an accretion disk. In the case of
yes.
stars, it comes with the natural evolution. have rotation and then evaporation to create a star. But in the case of other stars, evolved stars, creating this accretion disk is not evident, because if you have a single star and it has been ejected material, you will have some accretion. So the point to get this accretion is gain a secondary, which is accreted material from the primary. Okay? So what people think has to do with variety or good results.
Okay, thank you.
So if we don't have more questions, maybe we can go with next speaker. Thanks again, Luis.
¿Vale? ¿Vale? ¿Me oís bien, no? La mía es Alberto Jornada Postdocs, esta de ahí. Bueno, como quieras, PowerPoint.
Okay, so now we will have our second talk of the second part of the day. So the next speaker will be Alberto Muñoz de las Heras. So he is a physicist from University Autónoma of Madrid. Then he made his PhD in Trento, in Italy. And after his PhD, he now coming back to Spain with a Confuturo project, and he chose this institute for his postdoc, and now he will speak us about optical simulators as well.
Thank you. First of all, I would like to thank the organizers for giving me this opportunity. I feel so grateful for them, and I feel like playing in the first division. So yeah, the topic of my talk is also the topic of the project that with which I won this Confuturo fellowship, which is variational quantum optical simulators. This is a picture of my host group, which is the Quantum Information and Foundations group, which is, or in short, QINFOG. And here I wrote some of the research lines in which we are working, like quantum simulators and nanophotonics, quantum computing hardware, and even quantum and quantum-inspired algorithms. Okay, so first of all, I would like to give you an overview of what I did before, right, of my previous research. I started doing research in physics in the Universidad Autónoma de Madrid. This is Francesca Marchetti, who was my master's thesis director, and we worked on interaction quenches towards the strongly interacting regime using Bose-Einstein condensates. So in these systems, there is something that is called Feshbach resonance, okay? And basically, you can tune the interaction between the atoms at will. I mean, you can even send it to infinity. This is called the unitary limit. Okay? Then, when I moved to Trento to do my PhD thesis, I worked under the supervision of Jacopo Carusotto. And some of the topics that we worked about was, for instance, abelian anyons in cold atomic gases. You know, if you have a two-dimensional system with strong interactions and you add a synthetic magnetic field, this system becomes a fractional quantum Hall liquid, and the the excitations, okay? The charged excitations are quasi-particles and quasi-holes, featuring fractional statistics that interpolate between bosons and fermions, and these are called anyons. Also, I work in a lot of topics related to silicon photonics, like, for instance, nonlinearity-induced reciprocity breaking to be used in optical isolators, lacing in nonlinear multimode resonators, four-wave mixing also applied in order to design broadband optical isolators. And this is also one of our, this is actually my co-supervisor of my thesis, which is Lorenzo Pavesi. And finally, I also work in topological lasers, okay? So by aggregating several of these circular resonators together, you can build quantum spin Hall lattices in which you have kind of an effective spin 1/2 for photons, and if you add a synthetic magnetic field and an incoherent path, you can have a topological laser. And we investigated that actually the sign of the kernel nonlinearity can be used in order to control the chirality of the laser emission. Okay, so now I move on to what I expect to work during my project here. So basically, we know that quantum technologies, which is this kind of technologies that exploit the laws of quantum mechanics, hold great promise. And I mean, some of their applications are very famous, like quantum computing that promises exponential speedups for certain tasks, quantum metrology, which promises to outperform the classical precision in measurements, and also quantum key distribution, right, to protect communication channels from external attacks. And actually, a lot of big companies are investing a lot of money into this area, especially into quantum computing. We have here several examples, like Volkswagen Group and Xanadu, which is a quantum computing business, but also some Spanish companies like BBVA or Santander. And most of the effort is being carried actually by big tech companies like Google Quantum AI, which actually has a quantum computer. And also, there have appeared a large number of startups that are getting a lot of money, also from IBEX 35 companies that want to appear cool, so they give a lot of money to these startups in order to develop quantum and quantum-inspired algorithms. And yeah, actually, a few years ago, we had the first proof of quantum supremacy, which now is called the quantum advantage for political correctness reasons. And this was actually carried out using the Google's quantum computer. Okay, so yeah, quantum technologies offers a lot of opportunities, but they also come with a lot of challenges. In the short term, we need to figure out how we can make the best out of existing devices, which are medium-sized. They only feature about 50 to 100 qubits. They are noisy because they couple to the environment. This is called the decoherence and can lead to loss of information. They are not error-corrected, and they have limited connectivities between qubits. And here you can find the most advanced architectures, which are superconducting circuits and trapped ions. They are called, this kind of devices, noisy intermediate-scale quantum devices for these reasons. And also in the long term, and maybe this requires a migration of platform, so maybe these are not the definitive quantum computing platforms, who knows. We need to scale up the current devices while reducing noise at the same time, implement error correction, because at the end of the day, larger systems are needed to make an impact in areas beyond the academic sector, like finances or drug discovery and all of this. Okay, so my project aims to contributing to these two questions. Why is it called variational quantum optical simulators? What is a variational quantum optical simulator? Well, first of all, what is a quantum simulator? These are highly controllable quantum systems that can be used to simulate the physics of more complex quantum systems. Okay? So for instance, if you would like to study electrons in a solid, this can be difficult because you can have noise, impurities, most of all you have a low degree of experimental control. But you can migrate to another platform like ultra-cold atomic gases, where you have a huge degree of control over the system with laser light, magnetic fields, all that stuff. And you can even design tailored Hamiltonians with a high degree of experimental control. For instance, the most celebrated example perhaps it's the Fermi-Hubbard model, in which you can tune at will the tunneling between the lattice sites and the on-site lattice interaction. Okay, and well, in the recent years, you have a lot of examples of this like you can simulate a 1D topological gauge theory using ultra cold atomic gases on quantum electrodynamics in a topological waveguide. Okay, so now quantum optical simulators. So we know what is a quantum simulator. A quantum optical simulator involves photons, basically. So in these systems we have quantum emitters, which can be neutral atoms, ions, quantum dots, excitons, whatever that interacts with light, coupled with photons that basically mediate interactions between the quantum emitters, okay? And here you have several examples of these systems, like photonic crystals, quantum emitters in optical cavities, atomic arrays, excitons in two-dimensional materials, trapped ions. And this kind of systems offer several advantages. For instance, you can profit from collective quantum effects, like super radiance, or even from topological effects, okay? You can place your emitters or your system in a certain geometry, okay? And you can profit from these super good topological properties like resistance to disorder and all that stuff. Okay, so the objective of... so now that we know what is a quantum optical simulator, the variational part comes from one of the objectives of this project, which is actually to develop algorithms that can be useful for current quantum technologies. And one way of doing this is to implement variational algorithms, okay? So this kind of algorithms, in this kind of algorithms you have a parameterized quantum circuit, okay? So you can have, for instance, single qubit rotations parameterized by the rotation angle, and also you need, like, for instance, 2 qubit gates that introduce entanglement into your system, okay? And finally, you give an input state to this circuit and you get an output state, okay? So with this output state, you can construct a cost function that will be given to a classical optimizer, okay, in order to be minimized. For instance, one of the most famous applications of this is the variational quantum eigensolver, which basically consists on minimizing the expectation value of some Hamiltonian that is complicated and relevant for quantum chemistry or condensed matter. And using the variational principle, we know that the cost function always has to be larger than the ground state. So by minimizing this, we get an approximation to the true ground state of the system. This is not the only thing that we want to do with this project. We also want to improve the scalability of quantum devices. For instance, by using that topological protection against the coherence, or by designing distributed quantum networks connected by topological quantum interconnects. Okay, so now I will be more specific, and I will explain to you some of the things that we have or are already developing in this context, okay? So this is work that we carried, mainly led by our PhD student, Christian, who is over there, so you can ask him if you have questions later. So basically, here we want to apply this idea of variational quantum algorithms to waveguide QED platforms. So the setup is a photonic crystal waveguide to which we couple the quantum emitters, okay, which can be driven by lasers, okay? And actually, in this kind of systems, you can have different effective interactions between the emitters mediated by the photons. So the emitters really don't see each other. What they see is the photonic crystal waveguide. And by virtue of these photons, they are able to see effective interactions between them. So depending on the level structure of the emitters, you can have different types of interaction. But overall, the general idea is that both the interaction strength and the range of the interaction between the emitters are dynamically tunable by means of the Raman pulse frequency and time span. Okay, the Raman pulse is given by the laser, right? By the laser pulse. So we have tunable range quantum gates, and we wonder if we could get some advantage using them with respect to traditional quantum circuit structures, right? So we applied this idea to a couple of condensed matter models, the XXZ model and the Ising model at a couple of critical points, okay? And the interesting part here is that at the critical point, the correlations decay as power loss. So we expected that this tunable range of interactions can help us to better approximate the ground state, okay? So actually, it's not the fact that we have a long-range interaction that helps. It's the fact that the range of interaction is tunable, okay? And we found that using this kind of fansets, we get better results with respect to the traditional parameterized quantum circuits that are widely used in the literature, okay? So now, beyond this, actually by changing the cost function, you can apply these algorithms to different problems, right? So this, what I showed you before, was an example of this variational quantum eigensolver. But in this case, we can also apply it to quantum metrology. I mean, we could use the variational quantum circuit to generate states that allow the best precision in a measurement while simultaneously being robust against noise, like photon loss and dephasing. So we know that there are different types of quantum states that can be used as proofs in order to measure quantities, and the best example of this is the null state. But the problem is that the null state is very sensitive to noise, because once you lose a photon, okay, the null state is this state, so it's this superposition. Once you lose a photon, you break the coherence, right? So there is a trade-off between the precision that you can acquire and the resilience to noise, okay? So we wonder if using these variational quantum circuits, we can get states that go beyond these null states and that are both resilient to noise and offer a great precision in measurements. Okay, so basically the system that we envision is having a couple of cavities, okay, and this will be the variational part, okay, because we can use, like, if you have a James-Cummings type Hamiltonian here, you can treat the parameters of the James-Cummings model as variational parameters for a variational quantum circuit. And the photons would be released, and here they will go through a Mach-Zehnder interferometer in order to encode a phase here that we want to measure, and then add noise, and then they will go through some detectors, okay? And actually, it is known that in the noiseless case, the best state is the null state that saturates the Heisenberg limit, which scales as 1 divided by n squared. Okay, so here I'm plotting the variance squared of this parameter as a function of the number of photons. And actually, the Heisenberg limit can only be obtained when you use quantum resources, like entanglement. If you use states without entanglement, actually you will get this other line that scales as 1 divided by n, which is called the standard quantum limit or short noise limit. Okay? Yeah, so this could be another part. So we have already the calculations for the noiseless case, and we see, and this is already a really impressive result, because what we are seeing is that we are capable of producing states that saturate the Heisenberg limit in the noiseless case for a huge number of photons, because it's not trivial how to produce null states or how to saturate the Heisenberg limit beyond a couple of photons. Okay, for 2 photons you have the Hong-Hu-Mandel effect, so you can prepare these states deterministically, but not for a number of photons larger than 2. And you see, we are able to prepare them for 20 photons. So this is already a good result. Another research line is nonlinear bound states in the continuum. Okay, so basically here we are changing completely the paradigm. We are migrating to another platform, which is semiconductor micropillars, okay, that host exciton polaritons. And here what we are doing is, this is some work that was developed by Alberto Amo and my boss Alex Gonzalez, which is over there. So they found out that by pumping, in this case, a one-dimensional lattice of micropillars, pumping it at 2 different positions, you can get a destructive interference that leads to light localization in the micropillar in between, okay? So actually, this system can be very well described by semi-classical equations like this, in which you account for the cavity laser detuning, the tunneling between the lattice sides, the kernel nonlinearity, the losses, and the coherent drive, which is the laser, okay? And so we started investigating this system Actually, you can engineer these tunnelings, okay, in order to generate different dispersion relations, like a cosine dispersion, or that actually can be found only with first neighbor couplings, and also this linear dispersion that includes long-range happings, okay. And here I apologize for the change of labels, but they are switched in both pictures. So basically what we found is that these bound states in the continuum, basically what you have is that if you start moving the tuning of the laser, you can compensate it with the nonlinearity, okay, which depends on the intensity. So basically you are compensating the power of the laser with the tuning, and you can make these bound states in the continuum exist along almost the whole band. Actually, they survive longer in the case of the linear dispersion, because the density of states is different, and for a cosine dispersion, which is the red curve, you have a larger density of states on the edges of the band, so it is more likely that you will lose the bound state, okay? And finally, the last point that I would like to talk about, which I'm also working on this in collaboration with Carlos Vega, which is also a PhD student in our group, is chiral multimode photonic waveguide. So basically, we are going back to this photonic crystal platform in which we have the topological edge modes that are propagating in a well-defined direction along the lattice edges, and these are coupled to quantum emitters. Okay, this is a problem that was already investigated by Carlos in this super interesting paper, and what we wondered is that now we can study the driven dissipative phases that appear in these topological multimode channels. Okay, so basically the edge hosts several modes, and this is the key difference with respect to previous works. And what we want to do is to couple emitters to the topological edge states, include some gain, which can be coherent or incoherent, losses, parametric processes, and then if we adiabatically eliminate the photonic bath, we can study the resulting steady states, which will be topological or trivial also phases that can feature or not topological amplification, and then study their dynamical stability against small fluctuations. And actually for this is something in which our group has a lot of experience. You can ask Diego, Tomás, Álvaro, and they applied it already to the problem of a Hatano-Nelson model, which features non-reciprocal couplings, and they were able to plot a phase diagram of the topological driven dissipative phases and study also their dynamical stability. And obviously the long-term goal is like including nonlinearities here, which is the interaction between the emitters, and this is a really challenging problem. It's not clear at all how to do this. I mean, we could use Woodfiller mean field theory, okay, or even tensor networks. And with this, I have come to the end of my talk. Finally, here I show you the take-home messages. So basically, state-of-the-art quantum technologies face important challenges. On the short term, we would like to make the most out of the existing devices. And for this, we have the variational quantum algorithms, like the variational quantum agent solver that I work together with Christian, and also the quantum metrology part in order to generate interesting states that can be used as proofs for sensing. And in the long term, sorry, we would like to also study promising platforms for quantum technologies, and this is the case of topological waveguide QED and also polariton micropillars. And with this I finish. These are my collaborators, and I thank all of you for your attention, and I hope that you have found the talk interesting. Thank you very much.
Well, thank you, Alberto, for this talk. Perfectly in time, so we have plenty of time for questions.
Yeah, it was a little too technical to me, the talk. No, this is a pity. But in any case, I think I follow you more or less. One technical question is, in what extent the Gutzwiller mean field theory is good enough? Because you were talking about density matrix, but I didn't see in your, probably I missed something. I didn't see the density matrix in your slides. What type of density matrix is there?
Okay.
Because there are many ways to factorize density matrix.
I'm not an expert on the Wheeler-Mansfield answers, but I know that it has been employed in several works related to this kind of systems. But I would have to investigate a little bit, because right now I really cannot provide an answer to you.
And the second question is, when you are using nonlinearities, if I understood well, you are using semi-classical equations, no?
Yeah,
like it's quite similar to, let's say, a Langevin type equation. Where's the noise there? There is no noise?
The role of the noise is played by the coherent drive, I believe. But it won't be a stochastical
Yeah, this is the
part.
point.
Yeah.
But the laser plays a stochastic role?
Well, it is the inhomogeneous term. So in that sense,
Okay.
they play kind of the same role.
Okay.
Only that in this system, it's not stochastical, as you said.
Okay, thank you. Very interesting to learn.
Thank you.
Yeah. Do we have more questions? No. Maybe I have one, but I don't remember which slide it was. I think it was
Before?
Oh no, this one. The next one.
Yeah.
Yeah. Because I haven't quite catches what makes the difference.
Between
Oh,
these
you can
two.
get yes to
Yeah.
reach the 1 to the n square limit.
Yeah, the difference is the quantum resources. So actually, you can only get the Heisenberg limit, which is the one on the bottom, using quantum resources like entanglement. So actually, this is saturated by the Nun state, which is this one. Okay, you see it is a superposition of these two states. But if you don't have entanglement, I mean, if you use a coherent state, for instance, which is a semi-classical state, you will get this other line. Okay.
I see, and depending of the success of how it works, it's possible to be in between these.
Yeah, of course.
Okay.
Of course.
And so you are minimizing.
Yeah, exactly.
Okay.
Once you start using quantum resources, you go down, and you only saturate the Heisenberg limit for this particular case of
okay.
the Nun state.
Okay, thank you. Okay, so, well, if we have no more questions, maybe we can go to the last speaker of the day. Thanks again, Roberto, for and
Okay? Okay? Like this is okay?
okay, so now we will start the last talk of the day. So the last speaker will be Carlos Cabezas. So Carlos Cabezas made his study in, his PhD in Valladolid, and after his PhD, he made quite a lot of postdocs, traveling a lot. He went to Tokyo, Valladolid again, to Taiwan, and since 2018 is now in our institute, and he will speak to us about rotational spectroscopy, how experimentally and theoretically he can gather this spectrum, and how it helps to detect molecules. So, please.
Okay, thank you, Alex, for the presentation. And thanks to the direction for the opportunity to stay here today. My talk is about the rotational spectroscopy that I used from 2007 when I started my PhD at the University of Valladolid. I apply this technique or this spectroscopy to the study of biomolecules, to the molecular structure of biomolecules, also to the study of molecules and reactions with atmospheric interest, like Krieg intermediates. And from 2018, when I joined the molecular astrophysics department or group at that time, I started to do rotational spectroscopy studies of molecules with astrophysical interest. Rotational spectroscopy is one of the most precise experimental tools to investigate the molecular structures in the gas phase. The rotational spectrum of a given molecule depends on the values of the rotational constants. These constants depend on the mass distribution that we have within the molecule, within the molecular structure. So the rotational spectrum can be considered exclusive for each molecule and is a fingerprint of a given molecule. So using rotational spectroscopy is possible to distinguish between the structure of different isomers, conformers in this case, tautomers like this, and also between isotopic species, even when the molecular chains or the structural chains are really small. Using different experimental approaches, we can observe the rotational spectrum in a wide frequency range that starts at the microwave region and go up to terahertz region, passing through millimeter and submillimeter regions. So we can observe the rotational spectrum of a large variety of molecules, with the only requirement for the molecules to present a dipole moment different from zero. Probably the most important application of the rotational spectroscopy is that to the molecular astrophysics. This is because when we observe an astronomical object using a radio telescope, we can obtain a line survey or a spectrum where we can see all the rotational transitions of all the molecular species that are present in the object that we are observing. So the identification of all the molecules that are forming this object requires the accurate knowledge of the frequencies of all the rotational transitions for this species. We can obtain this information if we do rotational spectroscopy experiments at the laboratory, where we can study and we can obtain the rotational spectrum of a single molecule. And then, with the help of the quantum chemical calculations, we can identify and assign every single line, every rotational transition. And then, after the analysis with a Hamiltonian, we can derive the molecular parameters of the molecule that we are observing. These parameters are the rotational constants, the centrifugal distortion constants, and also hyperfine constants, depending on the molecule that we are considering. If these parameters are accurate enough, we can get predictions in the same frequency range that we are observing with our telescope, and we can directly compare both spectra. Comparing by the direct comparison, we can identify one by one each molecule in this object. around 95% of all the molecules discovered in the interstellar in the space have been identified using this methodology. My research in the institute from 2018 develops in the context of rotational spectroscopy and molecular astrophysics. And my research activities are summarized in these 3 points. On one side, I do rotational spectroscopy experiments using the Gazella experimental setup that I will show in the next slide, of molecules that are candidates to be detected in the space. In a second type of experiments, I try to generate and characterize, using rotational spectroscopy, different unstable species with astrophysical interest. This part of my investigation is done in collaboration with NYCU University in Taiwan, in particular with the laboratory of Professor Endo. And another part of my investigation is dedicated to the detection of new molecules in space using quantum chemical calculations. Well, Gacela, that means gas cell for laboratory astrophysics, is an experimental setup that was built in the Yebes Observatory in 2017-2018 under the context of the European project Nanocosmos. This experimental setup is dedicated to the study of molecules and molecular processes using high-resolution broadband rotational spectroscopy. The design of this experiment is very new because it was the first laboratory experiment that used the same receptors used in the radio telescopes to detect the molecular emissions in a laboratory. The design is the one shown in the pictures, and the experimental setup consists of a vacuum chamber that is almost 900 millimeters length and 50 millimeters diameter. This chamber is connected to a vacuum system that is formed from a scroll dry pump and also a turbomolecular pump. And in this part, we have the two receptors in the Q band and the W band. And in this part, we have the fast Fourier transform spectrometers that are used to process all the signals that receptors can detect in the camera. With this spectrometer, we can observe the rotational spectrum in the Q band from 31 to 50 gigahertz and in the W band from 75 to 116 gigahertz of all the molecules that we can introduce in the chamber. When we want to study a rotational spectrum of a given molecule, what we do is to fill the camera with the sample that we want to study. The typical pressure is around 710 to -3 millibars, and we work in a continuous flow. That means that we are injecting the sample, and at the same time, we are evacuating using the vacuum system, just to avoid the composition problems of the sample inside of the camera. The measurements are usually done at room temperature, or we can heat the camera, the chamber, up to 350 Kelvin, so we can measure vibrational excited states as well. And usually we work with gases and liquids, but we can observe the rotational spectrum of solids with high vapor pressure. The camera is equipped as well with 4 UV lamps that are emitting at 183 nanometers, and they can be used to the study of photodissociation processes inside of the chamber. And also we can produce cold plasmas using a coil connected to a radiofrequency source. These are some of the molecules that we have studied using the Gacela experimental setup. All of them are molecules that are candidates to be observed in the space. For some of the molecules, the rotational spectrum was observed before, like is the case of ethyl methyl sulfide. This molecule was investigated up to 26 gigahertz in 1981 by Adachi et al. And these are the rotational parameters determined in this experimental work. If we want to do astronomical search of this molecule, we need frequency predictions in the range of 3 and 2 millimeters. That means in the frequency region from 75 to 116 gigahertz and from 130 to 180 gigahertz. If we use these constants to get the predictions, we get the frequencies. These are the frequencies for 4 of the most intense lines in these frequency ranges. But the uncertainties of these predictions are very large, close to 10 megahertz for lines in the 3 millimeter region and more than 40 megahertz for 2 millimeter regions. So that makes impossible to do an astronomical search because we don't really know where the lines are. But we did the study of this molecule in the range of 75 to 116 gigahertz, and we were able to observe more than 400 rotational transitions for each of the two conformers, the anti and gauge conformers. We also observed the vibrational site states that it's important to observe and characterize the vibrational site states because they contribute also to our astronomical observations. These are the data that we derive from our analysis, and as it can be seen, the rotational constants are almost similar, but the uncertainties are much smaller, close to 2 orders of magnitude smaller than those reported in 1981. Using these rotational and centrifugal distortion constants, we obtain accurate predictions in the 3 millimeter frequency range. The uncertainties are close to only 10 kilohertz, and in the 2 millimeter region, the uncertainties are close to 60 kilohertz. Our predictions are accurate enough up to 250, and using these predictions, we were able to do an astronomical search in 2 objects, Orion and Sagittarius B2, using our data from the 30-meter telescope, but we couldn't observe any of these species in our astronomical searches. However, all the parameters determined in this work can be used or will be used in a future search in these sources or in other objects. A similar work done using Gazella is the study of the cyclopropane carboxaldehyde molecule. This molecule has also 2 isomers, and in the picture you can see a small region of our spectra observed with Gazella. As you can see, there are a lot of lines. They are coming from the trans isomer for the ground state and also for 2 vibrational states, and also in here we can observe rotational transitions for the cis isomer. After the analysis of our rotational data, we were able to identify the ground state of the trans isomer and 11 vibrational states for this isomer. The accuracy of our constants, our experimental constants, is good enough to have good predictions, and even for the cis isomer, where we detect the ground state, and the observations were limited to 6 vibrational site states. With these parameters, we obtain good predictions up to 300 gigahertz, and then we carried out an astronomical search in the same objects, in Orion and Sagittarius, but we couldn't observe any of these species in our search. Another type of experiments I do are dedicated to the generation of unstable species, molecular species with astrophysical interest. With unstable species, I mean all the chemical compounds that cannot be synthesized in a laboratory using organic or inorganic chemical routes and then storage in a bottle. Okay, if we want to observe the rotational spectrum of unstable species, we need to generate them in situ at the same time that they are characterized in the gas phase. To do this kind of experiments, we use the FT microwave spectrometer of Professor Endo in the NYCU University in Taiwan. And this spectrometer is completely different from Gazella. It consists in a vacuum chamber with 2 spherical mirrors, and on the back side of one of the mirrors we have this device that is an electric discharge nozzle that can be used to generate unstable species in the gas phase. Prior to run any experiment, we need to prepare a gas mixture of a buffer gas that usually is argon or neon, And then we have to choose the chemical precursors to synthesize in the gas phase the new molecules that we are interested in. The experimental sequence starts with a gas that crosses this section, this region. The gas passed through a very small nozzle or hole with less than 1 millimeter of diameter. And when the gas is crossing this part, we induce an electric discharge between two electrodes, and this discharge starts the chemical reaction between the chemical precursors that we have in our sample. Then the molecules, the new molecules go into the camera and they form a supersonic expansion because there's a big difference between the pressure inside of the cavity, close to 10 to minus 7 millibar, and the pressure of the gas. The supersonic expansion is a collision-free environment and is perfect to measure the rotational spectrum of unstable molecules because due to because there's no collisions, the molecules are stabilized. So when the molecules are inside of the cavity, they are proof by microwave spectroscopy. We detect the molecular emission and we obtain the rotational spectrum in the frequency domain. This experimental sequence takes only 40 milliseconds. So the philosophy of this experiment is repeat 100 or 1,000 times the same cycle to get a good signal-to-noise ratio spectrum for the analysis. This is one of the molecules, unstable molecules, that we have identified using this experimental technique. The name is 1-cyanopropyl radical. This molecule cannot be obtained commercially, of course, and it was prepared in gas phase using a mixture of methyl cyanide and acetylene in these proportions, both diluted in argon. We were able to observe a total of 12 rotational transitions, and here you have an example of 2 of them. As you can see, each rotational transition is split in many hyperfine components because this molecule is a radical with 1 free electron that interacts with the nuclear spin of this nuclei, with the hydrogens and with the nitrogen. And that's why each rotational transition appear with many hyperfine components. The analysis of this type of spectra is not trivial, but if we can get a good fit or a good analysis, we can get a list of molecular parameters that describe perfectly these hyperfine patterns. The comparison of the experimental determined constants is with those predicted by ab initio calculations allow us to identify this molecule in the gas phase. Then, as we do with other molecules, using these experimental parameters, we predict at the observational range the rotational transitions, and we compare with our observations. This is an example. In red we have our predictions, and in black is the line survey on the molecular cloud TMC1 that was obtained with the Quixote line survey. And in this case, we cannot conclude that this molecule is in TMC1 because there's not a coincidence between our predictions and the observations. Another molecule that was formed using electric discharge and characterized with FT microwave spectrometer is the deuterated species of the H2-CCN radical or cyanomethyl radical. This molecule was identified in TMC1 in the 90s or in the 80s and is one of the most abundant species in the interstellar medium. So we wonder if the deuterated species of the radical could be present in TMC1. So we ran the same experiment using methyl cyanide and deuterium diluted in argon, and this is a part of the spectrum that we observed. This is the 101000 transition, and as in the other case, it appears split in many hyperfine components. From the analysis of the spectrum, we obtain these molecular parameters that with very, very low uncertainties, and the comparison with the theoretical data is also good. Using our experimental parameters, we make the prediction for the next rotational transition that appears close to 38 gigahertz, and we directly compare with our observations from the Quixote line survey. In this case, we can reproduce perfectly some observations in the region of 37 gigahertz, and this allows us to claim the detection of this molecule in TMC1. And to finish, I show an example of how to detect a new molecular species in the interstellar medium using only quantum chemical calculations. The spectra from this figure show two groups of lines that were observed in the molecular cloud L4A3. All these lines were not assigned to any chemical species, and the hyperfine pattern indicates that all these lines could come from a molecule that is a radical. From the relation between the frequencies, we derive value for the B plus C, that are two rotational constants, B plus C over 2, around 36.1 gigahertz. So this number gives us some information about the geometry of the molecule. Using quantum chemical calculations, we predict this value, or B plus C over 2, for all the candidates that we believe that could be the carrier of this group of lines. As you can see, the most promising candidate was the radical H2NC, whose value is very close to the one determined from our observations, but the conclusive identification of this molecule cannot be done only comparing this data. So we need to analyze all the observed lines, as we do when we have a spectrum in a laboratory, like if was observed in a laboratory experiment. So from the analysis of all these lines, we determine all these rotational parameters that perfectly reproduce our observations in this molecular cloud. Then the comparison with the theoretical data allowed us to identify this radical H2NC as the carrier of these lines. This is an alternative method to identify new species in the interstellar medium when we don't have the laboratory data necessary to compare with astronomical observations. And this is the case of H2NC, that is a high energy isomer of this radical, H2CN, this one. And this radical has never considered in any laboratory or astrophysical investigations on the only way to detect this molecule in space is by quantum chemical calculations. We have applied this method to identify other species in TMC1, like these cations or a negative ion, also the radical HCCS+, and metallic species in another source, like IRC 10-16, that Luis talked about before, and these four radicals and this molecule that is a closer species. And that's all from my side. Thank you very much.
Well, thank you, Carlos, for this interesting talk. So, do we have some questions? Oh, a lot of them. Oh. My God.
Very interesting talk. I have only two technical questions. The first one is, which is the lifetime of your radicals?
Sorry?
The lifetime of your radicals.
I don't
lifetime.
Lifetime. not sure, but probably a few milliseconds.
So you have to carry out the experiments in less than this.
Yeah. The total sequence I saw is 40 milliseconds.
Yeah.
But there's most of the time you have to wait between the one excitation pulse and the recording on the molecular emission.
Yeah, but the point is you have to know in advance the lifetime of the radicals, no?
No,
no?
Not really.
Why?
Because the experiment is limited by the electronics, not by the lifetime of the radical. So to increase, for example, to increase the intensity of the lines, you can move your pulse sequence. But if the lifetime of the radical is smaller than the time that you need, you cannot observe the radical. This is what happened, for example, with the radicals that are open cationic species.
Okay.
Probably the lifetime is much smaller than the speed of our experiment. But for radicals that are neutral, we guess, or at least we can observe the signals. We don't know about the lifetime, but we know if we can observe or if we cannot detect the signals.
Okay, long time ago, a long time ago I was working on rotational excitation, bidirectional excitation. I am missing probably, I don't know, because I have seen one of your Hamiltonians. There is no interaction between vibrations and rotations. Right. I remember, for example, Van Vleck, long time ago, tried to take into account the interaction between, for example, the centrifugal distortion and so on. So how are you considering this?
Vibration, rotation,
the interaction
interactions. For some complicated molecules, can be you can get some information.
It's very important.
But in this case, in most of the molecules that we observe, if they are closal species, or if we only have observed the vibrational, the ground vibrational state, we don't have these problems. Probably in some molecules with internal rotation, molecules with a methyl top, you can have these kind of problems, but not in. I never study a molecule when I consider that. Not in my case.
And the last question is, you were talking about hyperfine structure and so on. So when you mention quantum chemical calculations, you have to include all these ingredients in your Hamiltonian. And it's sometimes not very clear, or it's not very well known, all the hyperfine. So how do you deal with this?
This is the most tricky part of the analysis. The predictions for some of the hyperfine constants is really bad. Using for example, you can only calculate with the Gaussian. With Gaussian, and it's like a lottery sometimes. Yeah. So sometimes the experiments are a benchmark for quantum chemical calculations. So it depends on the radical. Usually for 2 sigma or 2a states, there's no problem. But we have some problem for a 3 sigma radical for the 8 CCS plus, where the prediction of one of the constants were completely different from our determination. But I don't know what is the reason.
Very nice talk. I wonder, perhaps I missed in the first part of your talk with the Gazella experiments, you mentioned that you use the astronomical receivers. What is the difference if you were using the normal receivers in a molecular laboratory? Molecular physics laboratory.
The first difference is that you can get you can observe the whole spectrum at the same time. They are broadband, and the other detectors that I use in the laboratory are limited to one frequency range. This is probably the most important difference. And then, of course, is the sensitivity. There's no. This is the more sensitive detectors I've ever used in a laboratory, And
what does it mean? I mean, in general.
I mean, in the experiments with Gazella, we detect the molecular emissions of the molecules, okay, directly. Yep. So they are extremely sensitive. In contrast, in the other laboratory experiments, we induce the radiation that we are going to detect. So we need to polarize, excite the molecules, and go and detect. Signals are also very weak, but they are stronger than the signals that we detect with Gazella.
Mm-hmm. Okay, thank you.
Yes, I was curious because you are showing all these spectra, and we know that in detection of microwaves and in the radio frequency domain, there is some use of some quantum technologies like Josephson junctions, and amplifiers have some importance in this context. I was wondering whether there is some crosstalk between quantum technologies and the instrumentation that is used here, or something that you are aware of?
No idea. I never hear about that.
It's not really.
No.
Okay, I was just wondering whether inside these machines there was something quantum or not. Okay, thank you.
The machines, you say, are quantum limit. They are the best amplifiers that can be built. They are high electron mobility transistors, and they are used factor 1.5, factor 2 about the quantum limit. That's allowed to detect, concerning the question about the sensitivities, putting numbers, signals of 10 to the minus 27 watt, even 6 order of magnitude below that. We can detect 10 to the minus 27 is 1 Jansky. Right, nowadays it is possible to detect micro Janskys. Okay, then they are extremely sensitive quantum devices.
Some more questions, maybe? Well, maybe I have one, small one, about the Taiwan experiment.
Yeah.
Because since you induce a reaction, I guess you can have several products at time, and so you detect all of them at time? Or
Yeah, but using the catalogs of the rotational transitions of all the molecules, we make a big scan and we identify all the lines that have been observed before. So then we only use for our analysis, or we are only interested in the new lines.
Okay.
Because when you use, for example, methyl cyanide with acetylene, you can generate more than 50 different species or more. So, yeah.
Okay. Okay. Thank you very much. So I think we have no more questions. So maybe, yeah. Thank all the speakers all the day.
Gustaría acabar con dos cosas. Vamos a ver, el instituto, por desgracia, tiene 3 sedes, ¿no? 121, 126, 126. Este tipo de cosas y participación es muy importante.